In this section, we're going to take a look at modeling real-world situations with trigonometric functions. So let's start with an example here that has to do with electricity, the electricity we have running through all of our buildings. It says the voltage on an alternating current can be modeled by a sinusoidal function, v of t, where t is measured in seconds and v is in volts. If the voltage alternates between negative 180 and 180 volts, and the frequency is 70 hertz, find v, the voltage as a function of time, and make a sketch of the function below. So a couple of things here. First of all, if you aren't really familiar with this concept, alternating current is the type of current that flows through our power grid. So that's different from what we call direct current, which is what you would get from, say, a battery. So when you plug a battery into a toy or something like that, the battery is what's called direct current, so it stays at this constant voltage. But an alternating current, it oscillates between negative and positive voltage very quickly. So that's what we have going on here. And then there's this new concept that you see here when it says the frequency is 70 hertz. Okay, so what's that all about? So for a definition here, we say that the frequency of a sinusoidal function is given by 1 divided by the period. Okay, so just over on the side here to help us understand this, period, if we're thinking of our x-axis here as time, which we are, we could interpret this as the amount of time it takes to complete one cycle. Okay, so just let's use seconds here. We would say this is seconds that it takes to get through one cycle. So the frequency is just the reciprocal of that. The frequency is measured in cycles per second. So in other words, if you let 1 second go by, how many complete cycles has the sine wave gone through? Okay, and hertz, when we say hertz, anytime you see that, you can assume that that means cycles per second. That's what it means. All right, so what I know is that if my frequency is equal to 70 hertz, right, that really means 70 cycles per second, then I automatically know at that point that the period is going to be the reciprocal of that, 1 over 70 seconds per cycle. So that tells me how long it's going to take in order for me to complete one full period. So let's go ahead, or one full cycle, excuse me. So let's go ahead and mark right here, I'll put it right here, 1/70th of a second. And I know that from 0 to 1/70th of a second, I should complete one full cycle. Okay. Now, we're measuring this as a sinusoidal function. Remember that sines and cosines are just shifts of one another, so it doesn't really matter if you pick sine or cosine, and they're not real specific here about where they want it to start. So at t equals 0, should it be at its max, its min, or right in the middle? That doesn't really matter. And if you think about a wave that is repeating every 1/70th of a second, we probably wouldn't care too much about where it starts. So I propose we just go ahead and use a sine function. Okay, so we would say here v of t is equal to, well, we need an amplitude, right? So the amplitude, since it's going between negative 180 and 180 volts, probably should just be 180. And then I'll put the sine, okay? And we've done this many times now. It's the sine of bt, okay? So let's keep in mind here that b is equal to 2 pi divided by the period. All right, we've used that formula a number of times. So of course that ends up being 2 pi times 70 over 1, which is equal to 140 pi. So I'm going to put in here 140 pi times t. So that will be my function that governs this thing. And so I'm starting, of course, if I'm using sine, I'm starting here at 0, 0. After a full cycle, or a full cycle, I should be at 1/70th of a second. So exactly halfway through, I will also be at 0, because I know how sine behaves. And I think it's worth marking this. So half of 1/70th would be 1/140th of a second. And I know halfway through here, I'm at my maximum. But of course my maximum is up here at 180. So I'm right there. And I can mark this, okay? Half of 1/40th would be 1/280th. And then halfway through here, okay, well, this would just be 3 280ths, right? Because of course 1 over 140 is 2 over 2 over 280, and then so this would be 3 over 280, and of course 4 over 280 you can check is 1/70th. And so now I'm down here at the minimum, which is negative 180. So that puts me down here, and so now I can make a sketch of one cycle of this very, very quickly oscillating wave, right? We understand that because it's repeating itself every 1/70th of a second, this thing is happening very, very fast. And so we're obviously zoomed way in on a very, very short time scale. In this example, we're going to try to find a sinusoidal function that represents the depth of water at a boat dock as a function of the number of hours after midnight, given that there was a low tide of 5 feet at 4 a.m. and a high tide of 13 feet at 10 a.m. And we're going to let 12 a.m. be represented by t equals 0. So we're going to come up with an equation, we're going to sketch a graph of this function, and then when we're all done with that, we're going to try to figure out at what times the tide's going to actually be above 11 feet. So first, let's just kind of get our graph all set up. I think it makes sense to just go ahead and graph a 24-hour period here. So let's go ahead and count by 2s and make a notch every time. So right here is 12 hours. There's 24 hours. And let's go ahead and put a couple other marks here. So here's 6, and then 14, 16, 18 right here. Okay, so that'll give us our keeping track of our time here. And let's just go ahead and label that t is in hours. And then up here we've got feet, of course. And so we got to go from a low of 5 feet to a high of 13 feet. So let's just go ahead and mark every one. And I'm going to stop here at 5 and go ahead and mark 5 because I know that's the low tide, so it's going to be an important value to note. 6, 7, 8, 9, 10, 11, 12, 13, and there's 13 way up there. All right, so let's go ahead and set about finding the important parts of a sinusoidal function. Maybe before I do that even though, let's go ahead and mark the 2 points that they gave us. They gave us at 4 a.m. we are at a low of 5 feet, and then at 10 a.m., so right here, we're at a high of 13 feet. So it's nice to get 2 points that we solidly know on this graph. So the first thing, let's go ahead and talk about the midline. what is our function, what line is our function going to oscillate above and below? Well, that's of course just halfway between this minimum and maximum value they gave us, so let's just average 13 and 5. 18 over 2, which is 9. So that means y equals 9 is our midline. So I can go up to 9 here, puts me right there, and let's do our best to make a nice horizontal dashed line to help us keep our bearings as we graph the function. All right, so there's our midline, and then of course amplitude. Amplitude is, well, that's going to be half of the distance from the low to the high, right? So the distance from the low to the high would be 13 minus 5, but chop that in half, and so we get 8 over 2, so that means our amplitude is 4. Okay. Now let's think about the period here, and maybe what I'll do at this point is go ahead and sketch go ahead and sketch what's going on between these 2 points, right? Halfway between 4 and 10, which would be at 7, we know that we're going to be right at our midline. And so I can go ahead and give a sketch of what is going on with our function between these 2 points. And so this, I can see, is not a full period from here to here, right? This is exactly half the period of a sinusoidal function, right? If I was to come back down and then finish again at that minimum, then I would have gone a full period. So what I know is that 6 hours is half of a period. So of course my period is equal to 12 hours. And for those of you who know about tides, that's not surprising at all, is that we have a period of 12 hours because you have 2 low tides and 2 high tides in a 24-hour period. So if our period is 12 hours, let's keep in mind what we're trying to do. We're trying to make an equation, and so recall that the b value in your sinusoidal function is going to be 2 pi divided by your period, which of course simplifies to pi over 6. So let's kind of write out what we've got so far. We have our function. It's a function of t, so y is going to equal the amplitude times our trig function, and I'm going to write cosine here, and I'll explain that in a moment. Cosine pi over 6. I'm going to leave a little bit of space in here, right, because we need to represent any kind of shift that's going on inside parentheses here. And then plus 9 for my midline. So now the reason I picked cosine is because the 2 concrete points they gave me are here and here, and I know that cosine, a regular cosine function at x equals 0 will be at its maximum. And so therefore, because I know a maximum value, it's going to be much easier for me to figure out the shift based on a cosine function than a sine function. Now I could have a sine down here and my function would look slightly different. It would still be correct, but I'm going to choose cosine because of that. So all I have to say to myself is, okay, this maximum point typically would be at t equals 0. So how far did I have to move it? Well, I had to move it over 10, right? And furthermore, what direction I have to move it? I would have had to move it right. And so I know when I want to go right 10, the way I represent that is to say t minus 10 inside the argument. So there's my function. And with that, I think I feel comfortable finishing out my graph. So my period is 12 hours, so that means 12 hours after 4 a.m., I should be back at my minimum again. And so that puts me over here at 16. Okay, and then halfway between 10 and 16, which would be at 13, I'll be at the midline again. And so I can go ahead and sketch that part of the graph. But I think what I would like to do is go ahead and finish graphing on this 24-hour cycle. So I know that another half period later I'll be at my max, so 6 hours later. So here at 22, I should be back there, and then right about here I should be at my midline, so I'll keep going there. Alright, and I guess I can just kind of finish this out and have it stop at about 24. And then over here, got something similar. We should probably be at 0 at half, or at 1/4 of the period, so 3 back, so that put me at 1. And so let's just kind of do something like that. So before we move on from this slide, let's do one more thing, which is to start to make sure we understand what we're looking for in terms of determining at what times the tide will be above 11 feet. So here's 11, and so let's understand that what we're doing here is saying, okay, when will this function that I've graphed have y values that are above 11 feet? Okay, when will that happen? So of course what I'm looking for is, okay, what time interval is it that I see this, right? And so in this 24-hour period, it looks like there's 2 different time intervals where that happens. Maybe it's not clear whether or not I have a little sliver over here or not. So I'll be open to however that algebra comes out. But here we have these 2 regions for sure. And so that's what we're going to be looking for. But of course, you need some more room for this, so let's go to the next page. All right, so let's start by rewriting what we had on the previous page. Right, we had y is equal to 4 times the cosine of pi over 6 times t minus 10 plus 9. And that was equal to y, of course, but then the y we know that we're interested in right now is 11 feet. So let's go ahead and set y equal to 11. So of course we can set about solving this. First we got to get that trig function by itself. So we have 2 is equal to 4 cosine pi over 6 times t minus 10. And dividing both sides by 4 gives me 2/4 equals the cosine of pi over 6 times t minus 10. But then of course 2/4 is a half, and that's kind of a good thing here because we know that 1/2 is actually a special value on the unit circle, so we can actually stay exact here. We don't have to reach for our calculator quite yet. So alright, when does cosine equal a half? Well, let's just sketch the unit circle, a real sloppy version of the unit circle real quick. We know that that happens in the first quadrant. Oops. Sorry, having trouble getting my pen color changed. So in the first quadrant right about here, right? And we also know the x value in the unit circle is 1/2 right about there. Okay, and so we should remember that that's, pi over 3. And then this one here is negative pi over 3. You could also say 5 pi over 3, right? It doesn't matter. I'm just going to use these. That seems pretty straightforward. So what I can now say then is, okay, this leads me to say that the argument inside cosine, right, pi over 6 times t minus 10 could be equal to pi over 3, but then let's keep all of our infinitely many solutions plus 2k pi. Or it could be equal to negative pi over 3 plus 2k pi. Okay. Now, of course, we want to know what t is going to be when the y value is 11. So we need to set about getting t all by itself. So let me again change pen color here, and we're realize the first thing we want to get out of the way is this pi over 6, right? So on both sides here, we can go ahead and multiply by the reciprocal. Remember, I'm multiplying both of these terms on the right side by the reciprocal. And 6 over pi on the left side of this one times 6 over pi here. And so as I of course get all this nice cancellation on the left of both sides of both of these equations, so these are gone. Let me put a little dividing line here. These are gone. And then I distribute this through to both of the terms on the right side. All right, so when I do that, I'm going to end up with these two equations. T minus 10 is equal to, so here as I distribute 6 over pi to pi over 3, the only thing that survives is 2. Okay, 6 and 3 reduce to 2 over 1, and then the pi's cancel. And then the pi's cancel here, so that means I am adding 12k. And then over here, same thing, but it's t minus 10 is equal to, it's going to be negative 2 plus 12k when we distribute through. And so the last thing, of course, is to add 10 to both sides. So we have t is equal to 12 plus 12k on the one hand, and then we have t is equal to 8 plus 12k on the other hand, where k is an integer. Now this is not quite our answer, okay? We've just figured out where the y value, or I should say when the y value is going to be at 11 feet, but we really want to answer when is the tide above 11 feet, okay? So let's go back to our previous page for a moment. Okay, so remember the two solutions were t equals 12 plus 12k and t equals 8 plus 12k. Okay, so let's see if we can find these. Well, this point right here certainly looks like it is at 8, right? And this point here certainly looks like it's at 12. So it looks like I've got this solution happening here and this solution happening on the other side, okay, when k is equal to 0. What if k equals 1? Okay, so if k equals 1, 12 plus 12 is 24. That puts me right at the end of my graph here, right? And then when k is equal to 1 here, that puts me at 20. That seems to put me right there. So it looks like what we're finding is that if we are between these two intervals, with this being the lower and this being the upper, then you're always going to be above 11 feet. So what I could say is, you know, since t was hours since midnight, I can read, you know, this is 8 a.m. to 12 p.m. and this is not, you know, 20, right? So what is 20, right? Well, 20 is going to be really, you know, this being midnight, so we can say this is 12 a.m. so this is going to be 8 p.m. So between 8 and 12, both in the AM and the PM, is when we're going to have a tide above 11 feet. So over here we can finish this by saying that the answer is we are above 11 feet between, I'm sorry about that W there, between 8 a.m. and 12 p.m. and 8 p.m. and 12 a.m. And so you can see how important it was, even in a situation where we're not necessarily looking for infinitely many solutions. You can see how important it was that I included this 2k pi term, because it led to the second solution, and we knew that there were supposed to be 2 in that 24-hour period.